All right, so okay, today we will discuss about having a kind of process control, some knowledge regarding on the process control, and the preparation of automated workflows for exploration and production wells will be part of that. And also virtual multi-phase flow metering based models will be part of that. And some validation and production regarding of some validation production we will mention already. All right. Okay, let's go. So the process control, when we if you would like to give some introduction regarding on the process control, the thing that we can say is it's an engineering mechanism that uses a continuous monitoring of an industrial processes operational variables. Example, what these variables? We already mentioned in the questions of the midterm as well. So temperature, pressure is part of that, rates is a part of that, and chemical contents even, including into this section. So, and the algorithms, and then use that information to what? To adjust variables to reach product output specifications and objectives. So process control can be a partially or fully automated system which is capable of maintaining the consistent product output. Okay. So one of the main mechanisms of this is we call control loop process. The process control is depend on the main mechanism which works this one. It's the control loop process we call, right? So control loop process, let's give an introduction about this. The main components of this control loop processing can be generalized as first sensors is a part of that. Okay, so what are the sensors? We gave the question we asked this question in the midterm. These are electronic or mechanical devices that gather the signals, get the data, and get these data signals to what? To send them to transmitters. To gather a real-time data, you have to send them via transmitters to the surface, or if it's a surface, you have to send it to RTU. By RTU unit, terminal unit, remote terminal unit, you have to send it via satellite or via any remote system. The signals has to be sent to the SCADA system. All right. So, and another one after sensors, it's coming to transmitters. Transmitters are electronic devices that send the different types of signals to controllers. A transmitter can send a small current through a set of wires. You can see the main controls of the control loop system in here. As you can see, it's a petroleum tank in here. Process fluids incoming, the fluids coming, and the maximum level which need to be recorded. Sensor is recording that. And then the flow transmitter is here, the control is here. And according to the situation, when it reaches to the maximum level, the process automatically send the fluids out, okay? Or giving an alarm that says that the tank is full, okay? So because why we need this one? If the tank is full, then it makes a kind of back pressure through to what? Through the degassing stations. And when oil comes through to, up to the well sites, it makes a back pressure and it creates a kind of reverse effect, and you cannot produce anything in this case. So I don't want my tank to be full, all right? So because of that, you have to be very careful. Sensors are making the things very easier by the day. We can say this. The signal types are categorized also as follows. Signals, we have different type of signals. One of them is the oldest conventional signal type. It's analog signal. So this is continuously varying physical quantity. The most common standard electrical signals is between 4 to 20 milliampere current signal, very few amount of current signal they have. So the second one is the digital one. It discrete values that are combined to represent the diagnostic, all right? So digital one is much more advantageous compared with the analog one in terms of the diagnostic and maintenance issues. The other one is the pneumatic and the differential pressure one. It's used to pump pressure to activate the controller. There are some tools, there are some valves, downhole valves using this thing. There are some surface equipments as well, surface tools as well, using this pneumatic and differential pressure, especially some multi-phase flow meters. I know they have a little bit high error percentage, but they are using this one in the pneumatic one in the field as well. All right, it uses differential pressure. Okay, so So the electronical devices with complex electronic systems and algorithms that operate the controller to act what? To act autonomous, right? Sorry. So controllers are categorized as first discrete. First discrete. What is discrete? When you put the controller as a discrete controller, it's enabled to have an on or on-off activation. For example, a valve setting that has only two operational positions, either open or closed. For example, we have a valve, Schlumberger was using that, called PCT valve. This PCT valve doesn't have any. It uses the discrete controlling mechanism. So it is, if it is open, it is open. If it is closed, then it is closed. And we have the right to use that one just 25 times. After 25 times, it's not, it cannot be used. All right. So we have to arrange it in a, we have to optimize the usage times of that during the operation, during the well test. All right. This PCT, it's a kind of ball which is opening and closing. Okay. If it is in this position, open part comes to the wellbore, open part comes to the wellbore side, to the casing side, tubing side, sorry. So then it's closed. When it opened, when hydraulically you communicate with that. When it opened, 100% it's opening and flow is coming direct. So you have just we could use that for 25 times. It's one of the oldest valves that we are using the discrete methodology, right? And the other one is the multiple discrete set points. So continuously, if it is continuous, then automatically complace the values of the input variables to the set point to determine if an error exists. For example, in PCT valve also it's happening. Sometimes we are thinking that we opened it, but the valve is not opening. All right, it's in the closed position. How you will do? You will match, if you open that, your flow rate, pressure, temperature will be changed in the surface when you compare it with the downhole one, which is in the lower position than the PCT. So you have a chance to gather you have a chance to understand that it is not working, then error exists. Okay. So an error is detected and the controller adjusts its output according to the parameters that were set up in the controller. Then, all right. So the other one is the fuzzy controllers. This is much a little bit more new technology compared with the continuous one. All right, actually, the valve settings allows an adaptive variable scheme of values. In this case, soft fuzzy areas to switch the control are particularly suitable for systems with high rate uncertainty. High state uncertainty. So this includes a little bit uncertainty, but it gives by using fuzzy logic. All right, it uses fuzzy logic, these controllers, and it gives you the chance to switch the control much more easier compared with the other one, right? Compared with the continuous and discrete one. So the next one is the control modes. Okay, so control modes, I gave here the control mode on, off, proportional, integral, derivation, and combination of all of these. So when for example, when we go for on and off means 100% close or 100% open. All right. So this is inexpensive. It's a basic mechanism. It's using for 50 years in the oil and gas industry. It's inexpensive and simple to install. All right. Disadvantage is the operating differential may be outside of the process requirement. In most of the times it's happening. So, for example, if you are dealing with the mid-range of companies, like for example, we are doing some jobs with some Hungarian companies, some Austrian companies maybe, then they are feasible. This type of tools are feasible for that. But if you go for Chevron, Exxon, whatever, so these tools are not the types that they are using. They want something real time and directly make the measurement. All right. So another advantage is accurate at the point of the control, exactly, and requires manual intervention. Definitely, this is correct. And the proportional is simple. For the proportional one, it's simple and stable and easy to install. High initial deviation from the set point and offset occurs near the set point. The integral, no sustained offset and requires time to overcome the instability. Yeah, but this is for the integral ones, it happens. Very precise compared to other control modes and possible increased overshot on startup. For the derivation type, we call it D, all right? For proportional, you will see P, integral I, and derivation D, all right? So there's a combination of these three as well. This is the latest technology tools, controlling mechanisms, by the way. So for the derivation one, derivation is the stable one, requires time to calibrate. Time to time, you have to pull out a fault. For example, if you are talking with the downhole, you have to pull out a fault. And rapid response to change and accuracy it has, but it's also giving some offset timing, which is if you are dealing with a certain drilling, for example, offshore drilling, which you need with your rig time is very important. So it's very hard to having an offset time because day rate of a rig. For example, if you are working in Africa, it's $200,000, $250,000, $250,000 per day. So because of that, each minute is very important in terms of money. So because of that, this we don't need any offset time. So derivation is not the way that we can use in this case. So there is another technology we called the combination. So they combined all these P, I, and D, proportional, integral, and derivation. So this is currently the best control mechanism. Complex to set up the entire system, but this is an advantage. It's a disadvantage. Complex to set up the entire system manually, but electronic controllers allow full automation of the system. And also it has a minimum offset and overshot issue. This is an advantage because I don't want to lose any time for this thing. But it is a little bit expensive. This is the this one is when you control with the on off. This combination is five times more the price. If you want to rent, for example, 1 month rent, 5 times more compared with the on off. So just want to give you an information regarding on this. All right. So achieving continuous control requires a combination of control modes, which are listed and described below. We believe that continuous control is an essential component of digital oil field systems. And as you can see here, if you want to go for a digital oil field system directly, you will go for combination cases. It's the most expensive, but it's the one that you can control and manage the best. All right. So the control modes, I will continue the chart comparing the performance of a valve being operated in 4 different control modes. In here, as you can see, proportional P, I, on off, and derivative D in here. There is no combination in here. This is before the combination invented. So as you can see here, for the set points, we gave the pressure intake values, all right, pressure intake values as I can say here. There is a new value set in 115 psi, and old set point was to 125. So when it comes to the proportional response gives some fluctuations in that. And in the beginning, it shows a decrease with a linear. It's showing linear decrease, and then fluctuates a bit again in the last times. Okay. When it comes to the integral response showing a real fluctuation all the time. Okay. When it comes to open on and off system, this is showing, as you can see, different values in here. As you can see, shows 125, 125, start to decrease, and then comes to 15. Show the response time. See, the response time is totally different than the others. So when it comes to derivative pressure, so it shows some fluctuations by time. But as you can see, how many counts it's arriving to the real point, okay, as you can see here. So integral response, it seems that integral response giving the best response compared with the others, right? And then second one is the derivative response, reached in 20, okay? It reached in 20, and it is the one of the best as well. So we can give all these. It's a good example and good combination and good comparison for all of them. All right. So from this point, let me continue. So for the proportional ones, the P ones, the valves and the controller are adjusted in different grades based on the change in the measured value from the set point. For example, if a piece of equipment reached a certain set point, the controller could close a valve by 25%. Okay, you can see when you check the plot. Also, you can see how the response is for proportional. When you come here for the proportional, as you can see, the time it's reaching to new set point is taking around 27, not even 27. It's reaching to in 31st, as you can see, maybe 1 in 27, and then fluctuate again and then reach in 31st. So it's taking too much time compared with the others. Okay, so the integral one, it operates at a rate proportional to the magnitude of the input steps. The derivative one, it delivers proportional increase or decrease of variable set as function of time. And rate action is function of the change speed. And yeah, this is the D1. So the combination one, which couldn't seen in this figure, is the best option for oil industry processes and the digital oil field systems. Generally, a combination of P and I is the best option. It's given as the best option because integral allows rapid change on slope and the proportional radius of offsets. When I come to the green one, the integral, as you can see how rapid it is changing. In 14th count, we already reached to the new set point, okay? When you compare it with others, on off, you can see on off is far away, it's reaching. So the best one is the integral response as we can see. So the benefits of integral response will be used in the combination one, all right? Okay, so after this one, let me pass to the next slide. So preparation of the automated workflows for exploration and production. So the first one is the motivation, which defines the business goals. All right. So the second one is the process to be automated. Identify the repetitive tasks, which one will be a repetitive continuously weekly basis, quarterly basis, 6 months or annual basis. And select the technology toolkits and CPU, what type of, in my digital oil field, what type of computer structure I will use. And then you will make your decision making regarding on your results that you take, you will make your decision making. And then you have to define your business metrics. What is your business metrics? What is your amortization time? What is your profit time? How many years you will invest your money in the initial case? In how many years it will take to pay that amount back? Okay, to get that amount back. So you have to describe all of these one by one. All right. So what type of engineering, exploration and production engineering processes should be automated? So main challenge of a manual workflow compared to the benefits of an automated workflow can be seen in here one by one. So here, actually, the workflow automation should focus on any task that can be done much more efficiently by computers than by people. So for example, what I can say, for example, computing oil losses and the gains for a field with 100 wells or more could require a person to enter values manually into a spreadsheet or database calculator. Sorry, I cannot close this now. Okay, calculator, all right. So because of that, it's take my time 3 hours or more maybe, right? So alternatively, an engineer could use a spreadsheet or a type of software coupled directly with a historian, your history matching, which gathers the necessary production data and use a batch allocation process to reduce the total time considerably, actually, okay? So, however, using cloud services, data analytics, and high performance computer power, this process can be fully automated and calculated continuously in real time, all right? It's a part of it's one of the benefits of the digital oil field. So from our collective professional experience, what I can say actually, most of the exploration and production workflows can be seamlessly automated, and particularly those workflows related to production and monitoring and surveillance and diagnostics and analysis, of course, of production events, production optimizations, and forecasting they can use. All right. So automation can be facilitated by a common platform for a data model that consolidates data sources and by the toolkit as well. So toolkit means a commercial or customized technical software. Okay. So this provides analytics, diagnostics, and the optimization to your client, or if you are operator, to your operator as well. You know. So examples of automated process or candidate process for automation I will give. So first of all, I can mention a continuous asset surveillance. Continuous asset surveillance include the well status, well is flowing, well is in injection well or shut-in position, or what's the position of your well, and the production uptime is included. The second one is the data cleansing and the high-level data filtering. All right. Third one is the estimation of production gains and losses against daily and monthly targets, even quarterly targets. So the other one is the production back allocation, real-time key performance indicators production monitoring. The other one is the priority upcoming of the well tests and artificial lift status and operational parameters, in especially some wells who are in the depletion period is very crucial. And we can say as an event notification in here for the asset optimization, the capacity constraint and the operating envelope is crucial to be described, and the flow assurance and the well integrity is another parameter, especially the integrity of the tools and the well itself, reservoir and your well bore is very crucial to be described, right? So the second one is the diagnostic and the analysis. So this version is requiring the minimum engineering support, okay? For the other one, if I require a strong mid-range or strong engineering support, then diagnostic and analysis will be a part of that, will be very important. It includes the filtering and conditioning data using the statistical approaches, data validation and reconciliation of the physical parameters, physical models, and well rate virtual metering based models. Okay, multi-phase flow and well and flow interval allocation is a part of that, important part of that. So well test validation and well model updates, another one. Well integrity and failure analysis, another one. Curve fitting, decline and type curve analysis, we are already familiar with the well testing, is another part of that. And rate and pressure transient analysis, again, a part of well testing, is another one that we need. So these are the repetitive tasks for requiring engineering supports, okay? All right, so another one, the optimization stage, it's again, we are in the engineering support type. So for this one, we can say that weekly production optimization and short-term forecasts are part of that, 1 to 7 days ahead, including the GL, electro-submersible pump, ESPs, and the progressive cavity pump, PCPs, and road pumps, RP, and other artificial lift methods, okay? GL means gas lifting, by the way, in here, I forgot to write it. And then monthly production optimization and long-term forecasts, more than 7 days up to month or quarterly basis also. So production back allocation and production and injection mass balance management is very important, very crucial. What is the volume that I already injected? What is the volume that I already produced, all right? So the balance of this one, especially for gas lifting, for example, is very important and crucial part, all right? So another one, repeated tasks that require engineering support and includes smart analytics. Smart analytics as follows. If our time is going, by the way, we have nearly 4 minutes, 3 minutes, whatever. If closed, please open again and we will finalize, okay? Okay, so forecast prediction analysis in here. Now I am in the smart analytic part, okay? I left the conventional part in one side. I am the smart analytic part now. So in here, my forecast for prediction analysis, I need intelligent alarming by exception-based surveillance. I need event recognition and diagnosis systems. I need identification and the tracking of well production opportunities. I need short-term failure detection for ESP, gas lifting, and road pumps, all right? Including early detection of the unexpected water production after water injection, especially because it's reaching to breakthrough. When it reaches to breakthrough, you can start to suddenly produce water. Then water percentage and fractions are increased. All right. So another one is a predictive advisory for short-term forecasts, production optimization, and long-term forecasts up to more than 30 days. And the production and injection management is a part of that. All right. So here, as you can see, exploration and production workflows. So automated workflows here are a series of processes programmed using what? Using a computing language that's capable of executing logical and calculation instructions with minimum human intervention, actually, okay? So one of my colleagues, we have a good relationship. We produced some papers with him, Dr. Saputelli, which is father of this artificial intelligence in oil and gas industry, intelligent wells. So these guys described a classic paper which showed the best practices of the digital oil field in the last 10 years. And they showed a series of technological which have origin. I will share this paper with you. The origin of the modern integrated analysis, actually. And this figure belonged to that paper that they had done. And it shows the main steps of the automated engineering workflow, which includes, for example, in the first part, the store information in a database. The second part is the filter and condition, cleans data, and extract high frequency and average data. The third one, send data to the various models and applications in the workflow, all right? Which can include both data-driven models and the physical model as well. Figure highlights the importance of these key elements actually in this figure, all right? So here, we can mention three different parts. One of them is the database and filtering technology and the engineering applications. So for the database, accessibility of the data through a database actually is the starting point of any automated workflow. It's very crucial. So for production workflows, a database is configured to link the data from different data sources, which include data from, for example, the different time frames and or frequencies, we can say. And select and organize the data and send it to technology for what? For filtering and conditioning, okay? So for the filtering technology, we can say that there are mathematical algorithms in the filtering, the second part, filtering technology. There are some mathematical algorithms which programmed either in standalone or web-based applications, currently web-based more, they are doing, are required to what? Required to perform the data filtering and cleansing, which was discussed in previously. We discussed this in week 3, okay? So many factors such as signal problems, data transfer, weather or environmental harsh conditions problem, or instrument errors and human interruptions contribute to errors in the raw data. Okay, so the filtering process is programmed to remove what? Erroneous data and the outliers and provide representative values for the data during the time period of the evaluation. Okay. So when the data is received, cleaned up, and post-processed, the main output is an average value of the raw data. That's actually the production rate, for example, Q, the production rate, pressure and temperature values at a specified frequency. So these values are automatically stored and then sent to various engineering software applications, okay? And the third one here, let me come, sorry. And the third one here, as we can see, what is the engineering applications. So in the figure, it's showed also what's showed the main options used by engineers, the data-driven models and the physical models. So data-driven models, which were already discussed we discussed this one Okay, so last time I started my recording. So we were mentioning about the engineering applications, engineer applications in the third category, okay? So we were saying what? We were saying that the main options used by engineers, the data-driven models and physical models, we said. And the data-driven models, which were discussed in previously in week 4, all right? Week 3, week 4. We are executed using statistics, data mining, data analytics, and application of what intelligent components which we gathered to make the decisions, with emphasis on more qualitative approach actually, okay? So to generate accurately meaningful trends and tendencies, okay, the data-driven models need what? Need the thousands to millions of data points to be gathered actually, okay? So the physical model, on the other hand, what we can say, it uses the physical law and the equations, which represents production processes and require only a few data points on averages. It's we can say daily average, we can say monthly average, or every 3 months quarterly average. Okay, so it is like this. So to generate the result, we need this. Okay. So this gives the software components of this exploration and production workflow mechanism. So let me give us one more detail, one more step into the details if we go. So we can say about the modeling of the decision-making process. You are making this, but how you are making this? So an automated workflow for decision-making should be designed in the same way as any cognitive process that is observe, understand means analyze, act, and learn. So here you have the signals. You have the signals from the sensors. You have to monitor it. You have the rules. You have to diagnose the rules. You have the smartness, smart materials, smart sensors, smart tools. You have to analyze all these tools and other things coming from that. You have to recommend, you have to get the recommendation, and you have to act on them. So for the cognitions also, you have to learn the cognitions and the steps and the limitations and any of the things related to these tools. You have to learn and you have to act according to that, all right? So in 2012, Bravo et al. Published a paper, and they have shown that the artificial intelligence component can be the key to enrich the cognitive factor in workflow automation. This actually taken from their paper, all right? So to assure optimal asset performance, automated workflows include the K phases shown in the figure and described as well already. I gave you, all right? So herein we have 4 different steps, as we mentioned. The diagnosis and analysis, it's 5, but diagnosis and analysis, I took it the same place. So first, you have to monitor in real time. The second one, diagnose and analyze. The third one, recommend and act, and learn and improve. So in the monitoring, in the real time, it displays the data time series on a dashboard with high definition screens. Okay, it visualizes and shows this data time series on a dashboard to show what the performance of the production over time by time passing in quarterly periods, monthly periods, or weekly periods. It shows you the performance and plots it. And these plots and graphical designs are set up with a series of rules with predefined monthly, actually, most of the time. And these monthlies cumulated in quarterly and yearly basis, all right? Or weekly basis, it starts, and monthly and quarterly it can go. Or daily, it can be targets, and maximum and minimum allowable or target values can be recorded as well. Different sections according to different needs, all right? So rules are used to estimate the absolute difference between the actual and the target values. The second one, the diagnose and analyze. The diagnose and analyze, sorry. So once exceeded any maximum or minimum allowable values, the system automatically diagnoses and classify any events, any anomalies, like the peaks that we show, that the frozen data or out of range, you remember, okay? Or any malfunctions, or the gauge sensor is not working, maybe, all right? And the workflows can be enriched with the fuzzy logics and the pattern recognition to allow engineers to be able to differentiate from abnormal situation to the equipment failures or data errors. Okay, data errors. So this is another important part, actually. So the other one is the third one. So I have 2 more slides. Now I checked. I have 2 more slides. Let's come into the end. So the third one is the recommend and the act. Okay, recommend and act. So in this part, the oil industry actually has decades to accumulated the field experience. We have, at least 60 years, 70 years ago, this started in terms of conventional oil production, not the old type. Okay, conventional structures has been built for decades. So the field has enough experience. So the engineers know how to act in a specific well issue, actually. So even though each well behaves differently than others, okay, the troubleshooting and what we can say the remediation process could be unique or slightly different from each situation. For example, for heavy oil wells, you know how to behave. Okay, for gas wells, you know what type of behavior. Of course, the situations can be changed from one to another, but you can describe the main procedure and behaviors. Okay, in first hand. All right. So well issues, mechanical malfunctions, and electrical equipment failures, okay, and any well anomalies actually have a recommended action plan with manuals. For example, in Schlumberger we have pressure manual. It says it gives all the details regarding on pressure, regarding on the cases that has been taken for 50 years, 60 years, whatever. Okay, so you already know most of them. Okay. So engineers use supporting tools such as what? Process models, statistical analysis, data mining technologies, expert systems, pattern recognition, and neural network tools, physical models, and as well as knowledge bases of the best practice and lessons learned. All right. So the automated workflow, what should be integrated with the process models, to capture the knowledge and create rule expert system. Okay, rule expert system. Now we describe this 50, 60 years. We already described what is going on. Now we are transferring all this knowledge, all these knowledge and experiences to machines, actually. All right, with the models, exit models, and the artificial intelligence. Okay, that's what we are trying to do. Okay, so in the last case, it says learn and improve. So in the final step as an optimal digital oil field system, decision making enables decision making process is to what? Is to measure, is to analyze and improve the action plan. Okay. This is the final step, learn and improve. So we believe that all aspects of a decision making process, including monitoring, analysis, actions, and most importantly, the positive or negative results should be recorded. Everything needs to be recorded. With current technology, recording the action plan is easy. If you record, then you can take the action. Okay, so you have to record in first case. So the challenge is how to process the recorded analysis and results, and then incorporate the learnings to update what? The automatic decision-making process. Okay. So even today, no consistent technology. Not a consistent technology exists to capitalize lessons learned without human intervention yet, but we are on the way of developing, especially the latest project that I talked to you, the KOC and Saudi Aramco projects are trying to deal with this one to make it monitoring and gathering data and recording, making it maximize and to transfer the decision making to what? To the machines. Okay, this is the main challenge. We are trying to do this, right? So automated in the last part, automated workflow levels for complexity or maturity. So level 1 is reporting what has happened, reporting systems commonplace in exploration and production. Level 2, analyzing why something happened, the queries, key performance indicators, and gaining popularity in exploration and production as well. In the level 3, predicting what will happen or why something might happen, analytical modeling, full physics model, and integrated asset management. Yeah, we will see in the week 6, we will talk, okay? And the 4th, operationalizing what is happening, continuous update, time-sensitive queries, and in database analytics on billions of raw data, we call big data, you know already. And in the 5th level, real-time decision-making to make the things happen, actionable data-driven real-time optimization, and very success with event-driven closed-loop integrated asset management and exploration and production. Okay. So these are the automated workflow levels for the complexity or maturity, we can say. So with this, this was the last slide, and with this one, I am finishing my presentation. Thanks for listening. If you have any questions, I will be glad to answer you guys.
Thank you, sir.
All right. So I recorded this one. I will share this one with you. Okay. I will update with a link. I will share this one with you. It will be beneficial for you for next steps for your exams. Okay. For final exam, whatever. All right. Okay. If all okay, then we can end the session. Okay.
Okay, sir.
Have a good day.
Okay. Have a good day. Take care of yourself. See you later on.
Thank you, sir.
Thank you.